All right, we're going to continue on in chapter 6, and we're going to talk about electron configurations. And electron configurations are pretty much an address system. It's going to tell us where each of our electrons are in terms of our atomic orbitals. We've got to remember here that we have our orbitals. We know that when n is 1, we have the 1s. When n is 2, we have our 2s and our 2p. And keep going, and we're going to take and we're going to fill our orbitals from the lowest and closest to the nucleus to the highest as we continue to go up. So if we look at our chart and we look at a multi-electron atom, and there's an issue with this because when we solved the Schrodinger equation, we solved it for hydrogen, meaning that we had one proton and we had one electron. And when we have one proton and one electron, we have find out that, for example, all the orbitals in n equal 2 have the same energy, meaning that this 2s and the 2p, if it were just hydrogen, would be on a straight line. But if we go into a multi-electron atom, the electrons interact with each other and these orbitals start to split. And we see this fairly obviously in the n equals 3. When we have a 3s here, the 3p is a little higher in energy, a little further from the nucleus. The 3D is even further than that. And note the 4s is actually a little bit below the 3D. So we're going to 3D, yes. So we're going to have to make a few adjustments in how we think about our electrons as they fill into the orbitals. So we talked about our quantum numbers, and we know that we have the first, which is our principal quantum number, and this tells us the level or the distance from the nucleus. We have our second quantum number, our orbital angular momentum quantum number, and this tells us the shape. And we have our S's and our P's and our D's. We have the M sub L quantum number, which gives us the number of orbitals. And an orbital is a 3D space that holds a max of 2 electrons. And we didn't really finish up our electrons, so we're going to finish up our electrons. Electrons are subatomic particles, and they have a spin, and we classify them as a function of the spin. And we are going to say that they have a spin up or a spin down, and we're going to label the spin up as a positive 1/2 and a spin down as a minus 1/2. In reality, we really can't tell which one it is. We just know if we put two of them together, one has to be up and the other has to be down. So we have rules. The first rule, and pardon my German pronunciation, is the Aufbau principle, which says that we are going to fill from the bottom up. And when we say that we fill from the bottom up, it means we're going to go from the 1s into the 2s, into the 2p, and we're going to go from the lowest energy to the highest energy. The other thing that's useful about this is it tells us that if we know where the electrons are, so let's say that we have 5 electrons, and we're going to add a 6th electron to this. If we know where the 5th are, we just put the 6 in the next available spot. Now, Hund's rule. Hund's rule holds for what we call degenerate orbitals. So this works for a set of P's or a set of D's or a set of F's. It only works for this particular set of these. So let's say that, for example, we have the 2p orbitals. Well, when we know we have the 2p, we know here that n is 2, we know that L is 1, and we know that M sub L has values from -1, 0 to +1, which gives us 3 orbitals. And we're going to take and we're going to diagram our orbitals out as boxes, where each of these are going to correspond to those p orbitals. Hund's rule says that if we have this set of p orbitals, where one of these would be 2px, 2py, and 2pz, we are going to put one electron in each of these before we turn around and start pairing them. So Hund's rule, one electron in each. And that only works for a given set of these before we pair. And the last rule is the Pauli exclusion principle. Now, the Pauli exclusion principle actually states that no two electrons can have the exact same quantum number. That's not how we interpret it. How we interpret it is that if you put 2 electrons in one orbital, They are going to be, one of them is going to be spin up and the other one is going to be spin down. So fill from the bottom up, put one electron in each orbital before you pair them, and if you have to pair them or when you pair them, you put one up and one down. So this is an energy level diagram for a multi-electron atom. None of these are ever going to be to scale, and we are simply going to take and we are going to fill up. So if we have one electron, we're going to put it in the lowest energy level. Now, we only go to the next energy level up or the next set of orbitals up if the previous ones are full, because that's got a good space here. So if we had to put a second electron in here, and we had, for example, 2 electrons, we would put one here already, and we'd add the next one to it. If we went to 3 electrons, we would take the first 2 that we know and put the third one up here. And then we're going to write the address for these. So for the 1 electron, we have 1 electron in the 1s, and we say that we have a 1s1 electron configuration, where 1 is the principal quantum number, s is the orbital, and this 1 here is the number of electrons. Now, there are multiple ways to learn how to fill these. These are one of the options, and if you've learned this or this makes sense to you, have at it. This makes absolutely no sense to me, so don't ask me to explain it. This is how I do it. I look at the periodic table, and I realize that the elements are grouped in columns, where this first column right over here are the S's. The second set of columns are the P's. These are the D's, and these are the F's. And we're going to fill from left to right. And then we're going to look at some numbers. The first row is a 1, period 1, period 2, period 3. And the first row of S's that we find is going to be a 1s. The first time we see P's is when they have 2 P's. The first time we see our D's is when we have 3 D's. And the first time we see F's are when we have 4 F's. And if we want to go, for an example, from a 2P to a 3P to a 4P, we just count our way down the periodic table. So, starting with hydrogen. We know that hydrogen's got 1 electron. It's going to put it in the closest orbital to the nucleus, which is the 1s. And when it puts 1s in there, it's going to be a 1s1. And this is the electron configuration for hydrogen. All right, so hydrogen. We know that hydrogen here is got 1 electron, and if we put it in the first orbital, it is a 1s1. We're going to have to keep our periodic tables out as we do these, so we keep track of which orbitals we are in, as well as which period we are in. So remember that these are the S's, the P's, the D's, and the F's. And if we look at these, it corresponds to the 1s, 2s, the 3s, over here, 2p, 3p, etc. And we're just going to take and look at our atomic number and see where we are on this periodic table. So if we go to helium, which has 2 electrons, we can imagine that it would exist right here. There's a few issues with the first row, but let's pretend it's there because that's the first set of orbitals that we have got. So if we draw ourselves out the orbital diagram, again, that's the boxes, and we put our electrons in, we're going to put 2 electrons in this. They are going to fill up the 1s before they go to the next level. And the next level we will see when we get to lithium. Now note, lithium exists right here on the periodic table, which tells us that its last electron is going to be in the 2s. How do we know? We know it from its position. We don't have to reinvent the wheel and figure out where the first 2 electrons are. We know where they are because they were in the same spot that they were in helium. So please note here that helium's electron configuration is 1s2. Lithium has 3 electrons. And as soon as the 1s is full, we're going to go up to the next orbital, and we are going to go to the 2s. And if we put 1 in the 2s, we tend to put them up. That's just tradition. It's not fact. We just put electron there. And when we look at our total electron configuration, we say it is 1s2, 2s1. This adds up to 3 electrons, and this is the electron configuration. It tells us where the electrons are in terms of their orbitals. All right, so with our periodic table in front of us all the time, we can go from lithium, and we can go over here to boron. Now, boron has 5 electrons. We know where the first 4 are because they're going to be in 1s1, 1s2, 2s1, 2s2 as we fill them up. So if we consider our orbital diagram, and we do it for boron, the lowest level is a 1s, then we go to the 2s, and then we go to 2p. 2p is slightly higher in energy. We fill from the bottom up, and we're going to go 1s2, 2s2. Now 2p is slightly higher in energy, which is why we don't fill it first. And we're going to put 1 in there, and we're going to say the electron configuration for boron is 1s2, 2s2, 2p1. Note this adds up to 5 electrons. So we can continue here as we go. So let's look at nitrogen. Now nitrogen is going to have a total of 7 electrons. And if we start and we fill from the bottom up, and we put them in, we're going to have 1s2, 2s2, and we've got 4 more electrons in. Now we're going to look at Hund's rule. Hund's rule says that if we have a set of p orbitals, we're going to put 1 in each orbital before we pair them. So that nitrogen here is going to be a 1s2, 2s2, 2p3, and it has 3 unpaired electrons. If I went to oxygen, I would put the next electron right here, and we'll see that. So continuing, if we go to oxygen, nitrogen, and fluorine, so if we have nitrogen here with 1 electron in each orbital, and then we add another electron to go to oxygen for a total of 8 electrons, we're going to take and we're going to put it right here. Now the little one-sided arrows are just a formatting issue. It doesn't matter if you do this or this, whatever makes you happy. It just implies that there's an electron with a spin up, and the key here is that if one's up, the other one has to be down. Now, we need to get our way all the way over here to neon. Now, neon is right down here, such that the entirety of the n equals 2 is full. So, neon has 10 electrons, and they are in 1s2, 2s2, 2p6. Now, this is the maximum number of electrons that can be held in the 1s. And this is the maximum number of electrons that can be held in the n equals 2. So n equals 1 is full, n equals 2 is full. And we're going to discover that we have some theories that go along with this. And one of the theories is that if we have a full n, we're going to have stability. That as soon as we fill up that n and we've got no spots here left in our levels, that our electrons are very low energy, they're very comfortable where they are, and we have a lot of stability. So let's do a few more. Let's consider sodium. If we look at sodium, we know here that the last electron is in the 3rd row down. It is in the s orbitals. And so if we start from the bottom and we fill up, we're going to go 1s2, 2s2, 2p6, again, 1s2, 2s2, all the way here through 2p6, and then go to the next row down, and we'll get a 3s1. If we continue here and we look at aluminum, aluminum is right here. We can tell from the position of aluminum that its last electron is in the set of p orbitals, not in the s's. We know that because it exists on the periodic table in the p's. And if we fill across, 1s2, 2s2, 2p6, 3s2, 3p1. And this is going to add up to our 13 electrons in aluminum. Now there is a shorthand and an easier way to do this. And the easy way to do this is to realize that we have stability. And we know that we have stability. Stability means that the element is going to be relatively unreactive, meaning the electrons are very low energy and very stable where they are. And one of the points of stability here is when we have this nice P6, is when our entire row or entire set of p orbitals is full. We also call this our noble gas configuration. So, quick note on stability. 1, a full N is stable. Note 2, a noble gas is stable. Continuing, a full PD or F is stable. Again, stable means unreactive, meaning the electrons are going to stay where they are. Electrons are going to be lost and gained until we get to this point of stability. The last one is at a half full. In particular, D and F, and to some tiny extent P, but a half full D or F is a little stable. So with that in mind, we're going to use a shorthand. So here's our shorthand. Our shorthand is we're going to go to the nearest noble gas, and we're going to use it for a set of what we're going to call core electrons. So let's start with lithium. We know that lithium is 1s2, 2s1, and we know that helium is the same as 1s2. Now we take the symbol for helium, He, and we put it in brackets, and this is going to be our abbreviation for 1s2. And we're going to say that lithium, instead of being 1s2, 2s1, is going to be helium 2s1. Now, why does that help? That helps because we immediately spot the point of stability, and it tells us that the electrons that are not inside of this stable core, we're going to call those our core electrons, are our reactive electrons, and we call our reactive electrons valence electrons. So if instead of having lithium, we had aluminum, and we know that aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. You go, okay, how does that help? Well, 1s2, 2s2, 2p6 is 10 electrons, which is neon. Now, we're going to use it to indicate that we have set of core electrons. We're going to put it in brackets. So we put a neon in brackets and then put the valence electrons on the outside. Now, if you remember, we learned our group numbers as that aluminum was in group 3. Where does this 3 come from? It comes from right here because aluminum has 3 valence electrons. 3 electrons after the noble gas core. We can do this for things that are significantly more complicated. So here, if we take a look at germanium. Germanium, if we consider this, is going to be all the way out after the 3d 10 electrons. So filling up, we're going to have to go from 1s2, 2s2, 2p6, 3s2, 3p6, and if we continue to go, and now we're in, as we find ourselves looking for germanium, we're going to be right over here. And we know that this group right here is the 4s. This group next to it is the 3d. And these right in here are the 4p's. We're going to go straight across for the sake of argument right now. And if we go straight across this, we're going to have a 4s2, these guys right here, 3d10, and then to get all the way to the last 2 electrons in germanium, we're going to have to do 4p2. Now, how do we sort out our valence electrons? The valence electrons are going to be the electrons with the largest quantum number. So what do we have here? We have a 1s and a 2p. Well, we know that's not going to work. Then we have a 3s, 3p, and a 3d. And then we have these guys right here, which are the 4. Now, the 4 ones are going to be our valence electrons. So we are going to regroup this. We're going to put our valence electrons on the outside. And we're going to say that our germanium is going to be our noble gas core. And you say, okay, well, why can't I go right over here? It's got to be the nearest full noble gas, which is argon. After argon, we're going to have the 3d10. Why do we put it there? Because it's got the same quantum number. This n equals 3. And we leave our 4s2, 4p2 on the outside. And we say that germanium has 4 valence electrons. All right, let's take a look at some transition metals. And so to get there, we're going to start out quickly here with calcium, and then we're going to need to do iron. If we look at these again on our periodic table, calcium is right here. and iron is right here. This is going to be the s orbitals. These are the d's and the p's. This corresponds to the row of 4s's, and this corresponds right here to the row of the 3d's. Now, if this was hydrogen, we'd fill the 3d's before the 4s's because the 3 is a lower number. This is a multi-electron atom. These get complicated, and we're just going to have to accept a few facts. And one of them is that we're going to put electrons into the 4s before we do them into the 3d. So if we look at calcium and we want to do its electron configuration, we're going to the nearest full noble gas, which is argon, and then we're going to fill across to exactly where it is right here, which is a 4s2. Now, if we go to iron instead is going to be argon, filling straight across the periodic table. It is going to be 4s2 3d6. Our rules still apply, which is the largest quantum number corresponds to our valence electrons, and we are going to rearrange. And when we rearrange this, we say that our iron is argon 3d6 4s2. And we can do that for pretty much all of our transition metals. So we've got a few weird exceptions. And one of our weird exceptions is chromium. Chromium, if we go straight across the periodic table, should be argon 4s2 3d4. You go, okay, why? Because it's 4 along into the 3ds. We know that the S's are going to be the valence electrons, so we're going to rearrange and say we have a 3d4, 4s2, again, the largest quantum number on the outside. And then we're going to go over here and say, oh, but it's an exception. It's not a d4, s2, it is a d5, s1. Question is why? And the answer is because a half full d orbital is a little stable. So what happens here? Well, what happens here is that if we look at our d orbitals and we have our 4s2, so if this is the 4s, it's got 2 electrons in it, and we have the d4, we're going to go 1, 2, 3, 4. This is almost like an empty seat in a movie theater where someone over here goes, aha, I'm crowded in over here and this is empty. And so this electron is simply going to take and shift over and go right there. Why? Because when each of these are separated, it is more stable. A half full D is stable. A full D is also stable. And there are other elements that do a similar thing. Silver especially will do. We fill it out. Silver exists right down here. It should be krypton 4d9 5s2, but that D here is a little bit lower in energy and a little bit more stable, and it shifts right over and it makes a full D10 5s1. Again, why? Because a full PD or F is stable, a half full is also a little stable, and the electrons will shift around to get stability. Do you need to memorize these? No. But if we ask you, you need to be able to explain them. All right, we can take these to some logical conclusions. So let's take and imagine that we have 10. 10 is Sn. It has 50 electrons. Now, at any point in time, you can always go back to 1s2, 2s2, 2p6, etc. Most of us just don't have the patience. So what we're going to do is we're going to take and we're going to go find ourselves the nearest full noble gas. Well, the nearest full noble gas is krypton, which is 36 electrons. So we're going to go to 36, and we're going to say that 10 is going to be krypton, and then we're going to fill from there. We're going to go to the row below krypton, and we're going to say that that's going to be 5s2, fill straight across through 4d10 into 5p2, and then rearrange so that you have your valence electrons on the outside, 4d10, 5s2, 5p2. And we can do this for any element on the periodic table. Now, continuing in, because the most important thing with our electrons is not necessarily where they are, but where they're going. So if we consider our representative elements, representative meaning groups 1, 2, 3, 4, 5, 6, 7, 8, and this is group 1, 2, and 3. These guys are metals. We know that metals lose electrons. The nice thing about our theory here is that not only does it give our electron configuration of the neutral, so if we look at sodium, sodium is neon 1s1, it's going to give us the electron configuration of our ions. Because metals lose electrons, we're going to ask ourselves which electrons are these guys going to lose? Well, they're going to lose the valence electrons, the ones in the outer shell. Outer shell, again, has the largest quantum number. So sodium is going to lose one electron. Calcium is going to lose 2 electrons, and aluminum is going to lose 3 electrons, which we know is consistent with the behaviors of group 1, 2, and 3. When they lose their electrons, they are going to only be left with their noble gas core. Why? Because the noble gas core is stable. So let's consider our nonmetals. We know our nonmetals gain electrons. And if we look at our representative elements, we can figure out how many, because we have group here 7, group 6, and we have group 5. Now, we know that's not stable. What is stable is group 8. Well, if group 8 is stable, then anything in group 7 is going to gain 1 electron, because 7 plus 1 is 8. Group 6 is going to gain 2, and group 5 is going to gain 3. So if we look at our electron configurations, this is going to gain 1 electron to make fluoride. When it does that, it's going to be a P6 or neon. Oxygen is going to gain 2 electrons. It will become oxide. It's going to go from a P4 to be a P6, which is also neon. Nitrogen is going to gain 3 electrons to be nitride, and it too is going to have the noble gas core, or just a noble gas configuration of neon. Again, why? Because it's stable. So we have a series that we call isoelectronic. Iso means same, electronic means number of electrons. And if we ask ourselves, what is isoelectronic with neon? The answer is going to be sodium and aluminum, fluoride, oxide, and nitride. Why? Because they all have the same number. Hopefully, we could throw in magnesium. So let's think about magnesium. Magnesium is going to be neon 3s2, is in group 2. We know that neon is stable, but these aren't. We know that this is a metal. So it's going to lose electrons. It's going to lose those 2 electrons. And magnesium 2 plus is also isoelectronic with neon. We ask ourselves, what's isoelectronic with hydride? Hydride here is going to be 1s2. The answer here is helium. Why does helium make why is it going to be helium core? Again, because helium is a full N equals 1. That's going to be nice and stable. Now, the transition metals are not necessarily quite as simple, but most of them make pretty good sense. So if we look at iron and we find its valence electrons, we know the valence electrons aren't the 3D, the valence electrons are the 4s. So iron 2 plus, one of the common ions of iron, is going to be argon 3d6. Now note, the more stable cation of iron is not iron 2 plus, it's iron 3 plus. Well, if we just continue pulling off electrons, we know that iron 3 plus has to be 3d5. Why is this stable? Because this is a half full D. Manganese is argon 3d5 4s2, and if we have manganese 2 plus, it's going to be argon 3d5. So what about some of the other ones? Well, let's think about zinc, and let's do silver, and let's consider lead and look at the 2 possible cations of lead. Zinc, we go across the periodic table, is argon 3d10 4s2, and I've already put the valence electrons on the outside. We always put the valence electrons on the outside because when we ionize it, this is a metal, it loses electrons. We're going to lose the valence electrons, and we're going to make zinc 2 plus, and it's going to be argon 3d10. Silver. Now silver, we're going to have to do a little vocab here. The ion, the cation of silver is diamagnetic. Now, diamagnetic means that all electrons are paired. Now, note here, the ion of zinc is also diamagnetic, but let's take a look at silver first. Now, silver should be krypton 4d9 5s2. No matter how you slice this, with the d9, this has unpaired electrons. If an element has unpaired electrons, we say that it is paramagnetic. But in this case, the cation of silver is going to be diamagnetic. Now we remember that silver is always silver plus 1. And if we write out our electron configuration and we do it straight off of our valence electrons, we think it should be 4d9 5s1, pulling off 1 from the outside. But that gives us unpaired electrons, and this has no unpaired electrons. So we have to imagine that that 1 up in the 5s, remember that's a higher level, is going to pop down to the lower level, giving us krypton 4d10. Again, do we expect you to know this? No, but if we tell you that Ag plus is diamagnetic, we're going to expect you to remember that diamagnetic means that all the electrons are paired, and certainly they are on 4d10. Now, lead. Lead is interesting because lead has 82 electrons. So we know we have to start with xenon, and xenon is 56. And if we fill our way across, we're going to go xenon, and then we're going to go over to 6s2. We're going to go into our Ds, and we're going to go into our 5Ds, and we're going to look at lanthanum, which is sitting here at a 5D, element 57. And then we go to the next element, and it's hafnium, and it's element 72. And we realize that we have stuff that's missing. Please remember that the inner transition elements have to fit into this mess someplace, and they fit in right here. We put one in the 5D, and then we go down to our Fs. The first row of Fs are the 4Fs. We have to fill the entire thing, and that is 4F14. We're going to go back up, and we're going to fill the rest of the Ds, and that will be 4D9. And then we're going to have 6S2. Yes, I recognize that's a pain. If we group this, we're going to have xenon, 4F14. Why is it first? Because it's the lowest quantum number, followed by, 4F14, 5D10, 6 S2, 6P2. If we make lead 2 plus, we're going to lose those 2 electrons. And if we make lead 4 plus, we're going to lose those 2 electrons as well, losing the valence electrons until we get a nice, stable configuration behind.